Yo, it's Dr. James Utley, your resident codebreaker data scraper, and I want to walk you through the next project here of Syndicate Laboratories. The science of code destruction and other synthetic delusions of the syndicate. All right, and that this one here it's been an idea that I've been working on for probably 3 years now, and it's called nucleogenesis. So it's a temporal framework for eukaryotic nuclear blueprint archival and reconstruction. Now that's a mouthful. What it means is taking data that we know through testing about a nucleus, and I've narrowed it down to a leukocyte nucleus, so a white blood cell nucleus. So that's either a lymphocyte, T lymphocyte, or it perhaps will be a monocyte or macrophage, and be able to take the information through the testing capabilities we have now to then reconstruct a nuclear blueprint file, or an NBM, a nuclear blueprint manifest is what I call it, and then use that manifest as a to uh, in the future when the technology presents itself, be able to reconstruct these nucleus, and therefore, from there, a lot of applications can happen. But I've really been thinking about this from a top down, a bottom up, and a top down approach. Okay, so what it means by that is like where it all started is I read this random research paper about how leukocytes can be trapped and essentially mummified in a dried blood spot card. So everybody's seen one of those dried blood spot cards. And so from there, it got me thinking, okay, well, if you're having some material that could be, potentially preserved for a long period of time, and we're going to say long in this context is like 10 years, and then, so you have that, which is essentially a dried white blood cell or leukocyte, mummified. Okay, then the next thing is, all right, if you paired that with some fresh testing techniques, and so to try to like really reproduce the architecture or a high fidelity chromatin architecture, and you did that simultaneously, or you did that relatively and then in the future when this technology does exist, then you kind of have a blueprint. Now to do that, in my mind, is that to build this nuclear blueprint manifest or NBM, you'd have to kind of look at this thing from end to end. And so with that is you just develop a pipeline, and that pipeline would is be composed of a sampler, which is how you maintain the you're going to do all the quality control stuff on the intake of the sample, which would mean like the dried blood spot card, all of the quality control that's needed to optimize the information that you're going to use for the NBM, and all of that. Right. So then you have an application that will take all that information, right, and then be able to develop a builder program, which is going to be able to kind of project and theorize via layer by layer how you could take information and then bring it to potentially real life, or you have enough information to bring to reconstruct a nucleus. Now that would also things that you're going to do a lot of simulations, and so there's going to be an application that's going to be looking at the reconstruction and to understand like what the uncertainty is. So you take the information, you try to predict an outcome, and then there's always going to be some level of uncertainty. Now, and then the last part is like, okay, you have this wonderful information file that has kind of the gaps filled in via predictive mechanisms, and that's either techniques of machine learning, and even having some aspects of it's statistics is going to fill in the gaps, right? So the most probable the most probable outcome in between to try to reduce uncertainty with the knowledge that you have. All right, so then at that point you have this file, the nuclear blueprint manifest, and then that manifest can then be forwarded to basically a synthesizer. So then you could synthesize this nucleus. In the future when we become smarter, or we operate in the artificial superintelligence world where that's possible. And okay, so I have been thinking about this for lots of years, and I have developed this white paper here that you're free to read. It's on syndicate-labs.io under nucleogenesis. And with that, I'll just go over a few things, as I know this is always the hardest concept for people to get. Like, what's the point? Why the fuck are you doing it? And I have spent a lot of time, but we're going to say, okay, so for example, we're going to take fresh material and we're going to test it, right? So here's the information. we have this is a table with the stability of nuclear information and how that carries after it's been dried out, essentially. And we have some analysis workflow of how this works. So you see that the one specimen goes for fresh testing, the other one ends up on a dried blood spot card for future analysis, etc. I have a breakdown of all the testing that would be probably required in this framework, and to build this nuclear blueprint manifest, the NBM. That's what we're looking for. And we see that this is what is the sample preservation and recovery matrix is going to be needed to then have this dual management. And dried blood spot cards was my initial thought. So that's what's sprinkled throughout this paper that is the mechanism for collection. And again, here's acquisition of fresh samples, etc. Like I pretty much try to spare no detail and go through a lot of the protocols as well as the predictive algorithms, etc. And I even threw in a kind of a crypto chain of custody because we know that this is going to take a lot of time. So there's going to be like a future, and so you have to maintain chain of custody. And right now, blockchain technology is probably the way to maintain it. That it has that it's open for people to verify via ledger, via public blockchain. The blockchain doesn't exist. So if somebody wants to build that, let me know, or I'll build on an Ethereum or something. Okay, and I wanted to show there was one other. This is a pretty dense paper, so take your time and read it. But this is the one. The aspect that I wanted to highlight is the multi-omics data integration and privacy layer model. And if you see that kind of everything stacks on each other, right? So we have the genomics, the epigenetic, epigenomics, the chromatin contacts, or the interaction, the architecture, transcriptomics, which is my gig, and then we have this what we're going to call an uncertain layer, which is like variable and noise, and just the uncertainties of the prediction. And I have it. You can go through each of these layers and understand. And I try to proof out the math, so it's if you think about that. But here's the legend of representation. So we have one from fresh samples, which is measured, then imputed, right? So it's like it's a calculated value, then predicted, which is like here it says 50-50, but maybe it's a lot less than that. And then placeholder, meaning like you just have no information, you're just using it as a placeholder value to maintain space. Yeah, you can go through this. There was one other diagram I wanted to show you. So this is total energy as we move through here with this algorithm. Okay, it's this 3D chromatin structure reconstruction model. So if you see that we're taking information, we're kind of trying to reconstruct the model. The part that I want to say is that that this is being what it's communicating here is an uncertainty scale, which means that we understand that there's going to be some great uncertainty. I think that's all I wanted to show you here. So this project is called Nucleogenesis. And I have made a YouTube video that's also on the same channel where you're probably watching this one, that goes over each of the applications. Because remember, there's a lot of synthesizing. Well, it's end to end. So to do so, I have to build these the nucleosampler, which is the intake of the sample, the builder, which is generating the blueprint manifest. So the nucleosampler is kind of a gatekeeper that says, okay, all the quality stuff has to be in place for it to then project a manifest. And then that manifest, you're going to say, okay, we're going to take this and we're going to simulate it for reconstruction. And then the next thing is like, okay, you have your final file, and then you could potentially synthesize that into a nucleus. But anyway, that is the white paper. I'm going to continue to work on this through this year. Yeah, it's very complicated, and I get it, and most people are gonna be like, what the fuck? Like, what the fuck is it and why? And I can't really tell you. I see that we have to have robustness in our archival to preserve material, biobanking material, and a dried blood spot card can easily be obscured. So if there was a calamity, it could be, as long as it's maintained in a case. And then also over long distances, right? So if you're trying to travel to Europa, if you had a blueprint, a digital blueprint of how you would reconstruct that nucleus, and then also the physical properties, then I think it would increase the probability that when you get to your next planet, that they would be able to reconstruct you a new body if your body has atrophied, so they can just preserve your brain. Anyway, this is pretty much what I think this is an amazing project. Of course, there's a lot to do still, and I think it's only limited by money. really. So that is nucleogenesis. So go check it out at syndicate-labs.io, nucleogenesis. And if you want to talk more about this project or what this means or anything like that, just find me on social media or something, and I would love to talk with you about it. And then remember, take them easy. Peace.